Okay, we'll cover the REEs that you wanted to go over. Before we do that real quick, just a quick background on these two sections that lead up to those REEs. Section 3 on kinetic energy, and then Section 4 on more kinetic energy. The purpose of those two sections is really to build up to a formula for what kinetic energy is. And pretty much every step along the way, they're trying to prove to you why the formula is what it is. So that's where all of the, all this nitty-gritty and all this data and all this discussion come from, is getting you to buy into and believe why the formula is what it is. And we talked about this yesterday with regards to how they set up this text. So what I wanted to really focus on for these sections is the relationship between kinetic energy and speed. When they walk through an experiment that they do to kind of build some data, again, just to prove to you what the relationship is. And you can see that as the speed increases, the speed of the wheel, so what they're doing is they're going back to this wheel. They spin this wheel, then they slow it down using an aluminum cylinder to build up thermal energy, and then they look at the transfer of kinetic energy in the wheel to the thermal energy in the aluminum cylinder. So what they're saying is, as the thermal energy in that aluminum cylinder increases, the speed of the wheel is going faster. But it's not a proportional relationship. That's the thing that they want you to note. So many of the relationships we've looked at are proportional. Like mass. Mass is directly proportional to kinetic energy. Mass is directly proportional to gravitational potential energy. It's directly proportional to thermal energy. And then distance is directly proportional to gravitational potential energy. This one is different. It's not directly proportional. What is directly proportional is the relationship of speed squared to kinetic energy. So that is a direct relationship. So essentially what that means, if when we get down here to the formula, speed has a much bigger effect on kinetic energy than mass does. Mass is more like 1-to-1. This is an exponential relationship. So as an object is moving faster, its speed has a much greater impact on the total amount of kinetic energy than any of the other factors do. Okay, so the fact that it's squared, there's that exponential relationship, that's one thing to kind of keep an eye on. I believe, just in reviewing the Chapter 13 test, there were maybe 2 questions which assessed that particular piece of content, where looking for the relationship between speed and kinetic energy and what effect the speed would have. So it's important to note that it's an exponential relationship. So whatever happens to the speed, you square that, and that's the effect it has on kinetic energy. Okay, so if the speed is 2, you square it, so the effect on kinetic energy is 4. Okay. All right, so let's look at some of these RAEs. I haven't looked at these yet, so bear with me. A compact car has a mass of 1,000 kilograms. What is its kinetic energy at each of the following speeds? Okay, so that's just straight up applying the formula. Okay, so we would do, the formula is half the mass times speed squared. So for kinetic energy, it's half times mass times speed squared. So we'd really just plug in the numbers at this point. So 1,000 kilograms would go in here for mass.
Good morning, teachers. In just a few minutes, we're going to have a guest on campus over in the teacher's cafeteria. He will be here pretty much all day to help you with your investment and retirement needs. His name is Eric Maniaci, and he represents VALIC. So if you want to come down and speak with Eric, he'll be in the teacher's cafeteria. Thank you.
Thank you. Okay, so we plug in 1,000, and then we just plug in the different speeds to see what the effect would be. So instead of wasting time doing the calculations, I'll just tell you how they, okay. Why don't, they don't even give, oh, wait. They don't even give the answer. Oh, they do, but they do it in scientific notation. Let's do it this way. So we'll plug them in. Okay, so 1,000 kilograms times 0.5 for half times, actually let me do 0.5 squared first. How do I do squared on here? We'll just do it like that. Oops. $125, is that what you guys got? Or am I doing this totally wrong? 125 joules. She just, yeah, in the book it kind of, why does it have it like this? The kinetic energy is about, yeah, okay, so I have 125. Yeah, the book gives it in a weird way, so if you're looking at it, you're like, oh, what are they talking about? I can understand why that was a concern. Okay, the book says 1 times 10 squared, 10 to the second, so an scientific notation, which just means 2 zeros, which means 100, which means they rounded it. It should be about 125 based on the way I calculated it. And the next one says 5 to the 4th, so what's that? With 4 zeros, that's 50,000. Let's see if that's what we get. 10 squared times 1,000 times half. Yeah, 50,000 joules of energy. So when you see, if you saw the answers in the book, it says 5 times 10 to the 4th, so 50,000 joules. And then for the one at 30, let's do 30 times 1,000 times half. So where's my zero go? 450,000 joules of energy. So in the book, they round it. That's why it's so confusing for you guys when you look at the answers. Yeah, so for 30 meters per second, the joules of energy should be 450,000 joules of kinetic energy. And then for 10 meters per second, what did we say it was? 50,000, which I guess you could just divide 450 by 3, right? Yeah, something like that. Okay. And then the half a meter per second was 125. So it's just a matter of plugging them in. I don't think the test asks you in scientific notation. The book just does that sometimes, just for fun, I guess. But yeah, as long as you can plug the numbers in and calculate it, then, I mean, you guys already took the test, but just thinking forward to the semester exam, I don't believe that they have any of their answers set up in scientific notation. So as long as you plug the numbers in and do the math correctly, then the answer should be there. Okay, so when would a car be moving at these speeds? Okay. I guess what they want you to do is describe the motion at 0.5 meters per second. I guess they want you to say slow. What do they want you to say? Oh my gosh. This is a silly question. They just want you to recognize that this is really super slow, like maybe driving through a parking lot. And again, how would you guys know? You don't drive yet, right? Okay. So 10 meters per second would maybe be driving through a neighborhood. 30 meters per second, maybe, what did they say for 30? I don't even know. I see, the thing is we don't relate to meters because we do miles per hour. So 30's fast, we'll just say that. I'm not really sure. That's probably a part of the question that I wouldn't include, just because it's not something you guys can relate to, so it's kind of strange. Number 10, can two people be moving at different speeds and still have the same kinetic energy? If you look at the formula, because there's more than one variable, they can be moving at different speeds and still have the same kinetic energy if their masses differ. So if it works out where mass is so much greater and the speed's slower, or speed's higher and mass is less, it could work out where they have the same kinetic energy and be moving at different speeds. Does that make sense? Okay. 11, can two moving cars of different mass have the same kinetic energy? Yes, again, it's the same thing. If their mass is different, we still have another variable, which is speed. So even if their masses differ, if their speeds are also different, they could end up having the same kinetic energy. Okay. Consider a cart moving at a constant speed. What will increase its kinetic energy more? Tripling its mass or doubling its speed? Without doing the math, I'm going to say doubling its speed probably, just because speed has an exponential effect on kinetic energy where mass is just more one-to-one. Let's see what the book has to offer. Tripling the mass will increase its kinetic energy by a factor of 3. Doubling it will increase its kinetic energy by a factor of 4 because of the exponential effect. So doubling its speed because of that exponent will have a greater effect than increasing the mass by 3. Okie dokie. Let's see. And you guys did 13.5, sort of. Did you guys understand it? That's the wheel, the spinning wheel. the big picture again with this chapter, and really what this whole experiment is getting at, well, if we go back to 13.1, here we were showing how gravitational potential energy will convert to thermal energy, right? So if we could calculate the gravitational potential energy of the water bottle by taking its mass and its distance from the ground and figuring out how much gravitational potential energy it has. By the time it hits the ground, all of that gravitational potential energy should be transferred to the aluminum cylinder in the form of thermal energy. So if it starts with 100 joules of energy, by the time it hits the ground, all of that 100 joules of gravitational potential energy would be converted to thermal. So it's like a 1-to-1. Should be, theoretically. So in this lab with 13.5, what they're trying to show you here is that gravitational potential energy can also be converted to kinetic energy. Okay, so it's not just gravitational being converted to thermal. There's other types of energy as well. So as this bottle falls, and again, we can calculate its gravitational potential energy because we can get the mass, we can measure its distance from the ground to know how much energy it's starting with. So then as it falls, it's starting to make the wheel spin. So again, it's going like gravitational potential energy is decreasing as it's falling, and as it's falling, it's making the wheel spin faster and faster and faster, so its kinetic energy is increasing. So by the time this hits the ground, all of its gravitational potential energy should be converted to kinetic energy. So then what they have you do is calculate, well, how much kinetic energy is there? So you time the wheel. You figure out the speed of the wheel, and then we have the mass of the wheel, so then we can calculate kinetic energy, and what we should find is all of the gravitational potential energy was converted to kinetic. And so we have all the variables to be able to, we can measure all the variables to be able to actually see how that plays out in a real experiment, rather than just talking about it theoretically. So that's why we do this lab, is so you can actually see it. You can see the bottle fall, you can calculate its energy, you can see the wheel spinning, you can time its speed, and you can do all the calculations just to support the law of conservation of energy, saying one form of energy will transform into another. It's not lost, it's not created. So the energy of the wheel isn't just coming from nowhere. It's coming from the gravitational potential energy of the bottle. And when the bottle hits the ground, and now all of a sudden it has zero gravitational potential energy, it's not that it was lost, it didn't just disappear, it was transferred to the wheel in the form of kinetic energy. So energy is just constantly changing form. That's really like the whole big idea behind this whole chapter. Okay, so let's look at 13, because this followed up that lab. Okay. Suppose that the bottle fell 4 times as far while attached to the hub of the wheel. So the distance we're increasing by a factor of 4. How would this affect the decrease in gravitational potential energy of the bottle? Suppose the bottle fell 4 times as far. Well, it would start with more gravitational potential energy, but it would still be decreasing as it fell. It would just have a further distance to fall, which means it would take longer for it to decrease. Let me see if that's what they're looking for here. Okay, yeah, what they're saying is if it's falling from 4 times further away, so the distance increases by 4 times, it's starting off with 4 times the amount of gravitational potential energy. So the amount of gravitational potential energy that it loses by the time it hits the ground is 4 times greater, because it started with 4 times more gravitational potential energy. So this is really testing your ability to understand how distance affects gravitational potential energy, that there's a direct relationship. How would this affect the increase in kinetic energy of the wheel? Well, the increase in kinetic energy of the wheel would then increase by a factor of 4. Because if there's 4 times the amount of gravitational potential energy, and all of it's being transferred to the wheel, then the wheel is going to have 4 times the amount of kinetic energy. How would this affect the ratio of the decrease in gravitational potential energy to the increase in kinetic energy? It will not affect the ratio. It still should be 1-to-1. Right? So all of the gravitational should be converted to kinetic. So still a 1-to-1 relationship. How would this affect the speed of the wheel? The wheel's going to spin a heck of a lot faster. If there's 4 times the amount of kinetic energy, then the speed will probably be twice as much, because if you think about that exponential effect. Mass staying constant, let's look at that real quick. So if we have kinetic energy is half the mass times speed squared. If this is constant, this stays the same. This goes up by 4, by a factor of 4 times 4. And if this stays the same, and we know that half, excuse me, is always the same, this 4, if you put it over here, kind of plug it in here, this would actually, the speed would actually be going up by 2, because 2 squared is 4. So the speed would double. Does that make sense? Did I explain that okay? You sure? Positive? You can ask questions. I know you guys don't know me as well, but feel free to blurt out and ask any questions. Okay. I mean, I think I make perfect sense, but I don't always. Okay. All right, so then they get into the law of conservation of energy, which we've been talking about throughout this whole thing. I do think, from what I recall, there were a couple of test questions that have to do with the spring as well. Oh, I hate when there's that glare. It's going to make it hard to see on the video. Okay. Again, these two scenarios are just reiterating the same exact point. But this time we're talking about, well, not with this one. This is still gravitational. This one with the spring. And it's really interesting. That's one of the reasons I love this textbook, because if we do these chapters in order, they introduce elastic force right at the end of this chapter. And then the very first thing lab you do in chapter 14 is elastic force. And it's funny because I skipped 13 and did 14 and 15 with my kids first and then came back. And so I'm looking at it, I'm like, oh, okay, that makes sense. So a lot of times the way they kind of end a chapter is where they pick up with the next chapter, which is interesting. But they're just showing, again, just yet another way of how energy can transfer from one form to another. Because with this wheel, what they have attached to the wheel is a spring. So when they kind of stretch the spring way up here, it's got all of this elastic potential energy, because stretching it is increasing its stretch. It's the force that you're applying to it. You're applying this force, so it's increasing its elastic energy, basically. So then when you let the wheel go, the spring, of course, is going to try to return to its normal state. And what that does is pull on the wheel and make it spin. So they're just, again, showing another example of how one form of energy transfers to another form of energy. So elastic potential energy converted to kinetic energy. Yes?
Do you have like the chapter 13 test?
I do.
Because like number 6 was like on that and I did not understand it.
Yeah, what I will do, and we could do this now if you want, after there was a few more REEs maybe we want to go over. I can't record it because then the test is out there and they're all crazy secure with that, so I can turn this off and we can go over. Yeah, I do want to go over that with you guys because I want you to see exactly where the little tricks were along the way, because there were some really tricky questions on that test. What were the other ones? Wait, I just had the little sticky somewhere. Oh, there it is, 17 through 24. Okay. All right, so here we go. 10 students whose combined mass is 700 kilograms ride down 30 meters in an elevator. How much thermal energy is produced in the elevator system by the loss in gravitational potential energy of the students? So all they want us to do here is calculate how much gravitational potential energy they had. So 9.8 times 700 times 30. So let's see what that is. 700 times 30 times 9.8.
You put the answer inside the notation.
They did, yep. I am not going to do that. It's about, my calculator says 205,800 joules. So it's just a matter of multiplying them out. We don't need to convert to scientific notation. I get why they do that, but really to understand the concept, that's not necessary. So 205,800. So again, just plugging those two numbers into the formula for gravitational potential energy. An object with mass m is moving at speed v. How is the kinetic energy of the object affected when each of the following takes place? Oh, this is a good one. Okay. M is doubled while v remains constant. So let's look at how each of these would affect it. Half times mass. And actually, I believe there was a couple of questions on here about how kinetic energy might be affected if you change the variables. So this is a good one. All right, so if this stays constant and this is doubled, then the kinetic energy will be doubled. So for A, the kinetic energy would be doubled. If this is halved while m remains constant. Okay, so let's plug in a number here. Let's just say we'll put in 4 just to see. What I like to do a lot of the times, if I'm not sure what the effect will be just by looking at it, I'll just throw a number in there, because the numbers always kind of tell the story, right? So if it's 4 squared is 16. Okay. Let me write that down, so 16. And if we half the speed, now it's 2. What? 2 is 4. I knew that. So 4, so it goes down by a factor of 4. So so if this effect normally would be 16 and now it's 4, so it's a fourth a fourth of what it would have. The kinetic energy would be 1/4 of what it originally was. Does that make sense? What I just did? You sure? Kind of.
Yeah.
Okay. So what I did was I just said, because looking at that, I'm not 100%, and sometimes I feel like I know. Sometimes I'm like, well, I think I could figure it out, but I really like to be sure. So just randomly throw a number in there and see what would happen. What if we made it? Excuse me. If we made this 6, let's say the speed was 6. So the effect would be 6 times 6 is 36. So let's say speed would normally, if the speed was 6, it would have an effect on kinetic energy of a factor of 36 because we square it, right? Okay, so let's say now we take this and we cut it in half. So now it's 3. So now the speed is 3. And that's 9, right? 3 times 3. Okay, good. So that effect would be 9. So how does it go down? It goes down by a fourth. You see how I did that? Okay, so I have to do that still too, because I just like to be 100% sure before I pick an answer or I provide information that, and so the numbers for me help out with that. So I like to just throw numbers in there when I can. If they're both doubled, okay, let's find a clean part of the paper here. Okay, so kinetic energy, half times mass times speed squared. Okay, so if we double this, it'll have double the effect. If we double this times squared, that's going to have 4 times the effect. So 8 times, does that make sense? So if we double this, it goes up by 2. If we double this, it goes up by 4. And 2 times 4 is 8. I wonder if I did that right. Let's see. Seems logical, right? Let's see. Yeah, it goes up by 8. And then if m is doubled and v is halved. So if we double this, it goes up by 2. If we, oh gosh, let's half it again. So see, I always have to plug numbers in because that exponential thing throws me off. Half, we said it goes down by a factor of 4. We already figured that out, right? It goes down, so it's a fourth. So if it goes up by a factor of 2 and then down by a factor of like 0.25 or 1/4, it'll end up being halved, right? So let's look at that again. Okay, so if this is doubled, it has twice the effect on kinetic energy. If this is halved, because we square that, so 1/2 squared, oh, that's another way to do it. 1/2 squared goes down by a factor of a fourth. So 2 times 1/4 is 1/2. So the effect on kinetic energy would be, it would have 1/2 the kinetic energy. Does that make sense? Okay, good. Good, good, good. And then m is halved, and v is doubled. Goodness gracious, they're making us work today. Okay, so half times mass times speed squared. By the way, I'm just using s instead of v. I don't know why they decided to throw v in there. I mean, I know why, but all it does is serve to confuse. Speed and velocity are numerically the same thing. The only difference is velocity includes direction, so we give it a different name. But I don't know that they even bring that up in this chapter, and all of a sudden they just start calling it v. I don't know why they would do that. Okay, so if m is halved, it's going to have half the effect on kinetic energy. If this is doubled, you double, right? You square that, so it has an effect of 4. So 4 times a half means it'll go up by a factor of 2. It'll double it. Good? Okay. Oh, I hate this question. All right, let's see. Okay, in figure B, a cart loaded with bricks can roll down a slanted board like the falling object in 13.1, heating. The cart is also tied to a fishing line wrapped around an aluminum cylinder, okay? Also in that experiment, a thermometer has been inserted into the cylinder. So it's, even though it looks completely different, it's the same concept as 13.1, where this is going to fall and it's going to heat up the aluminum cylinder or something like that. When the experiment, let's see, when the experimenter can change how much the experimenter can change how much the board is tilted. When the board is less steep, the cart travels a longer distance for the same decrease in height. Okay. And the table below shows the results of several runs. So here's the distance that it's traveling. The decrease in height is exactly the same. That's interesting. Increase in temperature is exactly the same. So it seems like the height is more important than the distance that it travels because the effect is exactly the same regardless. Okay. And which run was the board vertical? So if it was vertical, they said it was, oh, vertical is just straight up and down, so it's this one. Because they said as it gets steeper, as it gets less steep. How did they say it? When the board is less steep, it travels further. So if it's vertical, it's traveling the shortest distance. So in run number 1, it would have been vertical. In which run was the board the least steep? That would be 5. Because as they kind of almost start to flatten it out, it has to go further. Which determines the loss in gravitational potential energy of the cart? The distance traveled or the decrease in height? It has to be the decrease in height because the change in temperature is exactly the same regardless. So this clearly has no effect on the temperature, which has no effect on the amount of thermal energy. Does that make sense? Because these don't change, and these don't change. So these are the two that are related, not this one. Does that make sense? Okay. Oh, good. That wasn't as bad as I thought. Okay. Suppose the friction in the wheels of the cart described in problem 19 was so great that it could not be neglected. How would this affect each of the following? The total change in gravitational potential energy of the cart. That's interesting. Okay, let's see. So if the friction was so great, what I believe would end up happening is some of that gravitational potential energy is going to be converted to heat due to friction rather than being converted to thermal energy. So you know how we've been talking all along about that one-to-one relationship? All the GPE should go directly to the thermal energy and should be one-to-one. Well, if there's so much friction between the falling object and the board, some of the gravitational potential energy is going to be turned into heat due to the friction. So some of the gravitational potential energy will be, we say that it's lost, even though it's not really lost. We know where it's going. But it's not being converted to thermal energy. So it wouldn't be, so let's say if it starts with 100 joules of energy, and maybe 10 joules of energy is lost due to friction, then only 90 would be transferred to the thermal energy of the aluminum cylinder. So the total change in gravitational potential energy. The total change in gravitational potential energy would be the same, because if it starts with a certain amount, regardless of what it's being converted to, by the time it hits the ground, all of it has been transferred somewhere. So the total change in gravitational potential energy should be exactly the same, regardless of where it's going. Let me just make sure. Yeah, it stays the same. Okay. The total increase in thermal energy of the wheels and the aluminum cylinder. So the thermal energy in the wheels of the cart, that's going to gain some thermal energy, right, because of the friction. And then some of it's going to go to the aluminum cylinder. So the aluminum cylinder will end up with less total thermal energy because now it's like being split, kind of. Some of it's going to the friction in the wheels, and some of it's going to the aluminum cylinder. Does that make sense? Okay. How do they explain that? Okay. And then the change in, okay, so I see what they're saying here. Let me rephrase this. It is being split. So let's say it starts with 100, like I said, 100 joules of gravitational. Let's say 10 of it goes to the friction in the wheels, and 90 goes to the thermal energy in the aluminum cylinder. That total amount is still exactly the same. It's just being split between in two ways, one going to the aluminum cylinder and some going to the wheels. But this is where it would have an effect. The change in temperature of the aluminum cylinder will not be as great because not all of the gravitational potential energy is going to the aluminum cylinder. Some of it's going to the friction in the wheels. So that's the one that would be different. Does that make sense? Okay. To quickly stop a car moving at a horizontal speed, that's this way, you must apply the brakes, yes. To keep a car at a constant speed while it is traveling down a hill, you must also apply the brakes. That is true. Again, you guys don't drive, so I love how they give you questions you can't relate to. Consider two identical cars, each having a mass of 1,000 kilograms. One, moving horizontally, is brought to a stop from an initial speed of 25 meters per second. Okay. The other travels down a 300-meter high hill at a constant speed and is not stopped. Oh, for heaven's sakes. Which car will the increase in thermal energy of the brakes be greater? Oh my gosh. All right, let's see. So I think what we need to do, let me think about this for a second. Okay, this one is brought to a stop. So we can measure the kinetic energy of this one, I think. Two cars having the same 1,000 kilograms. The initial speed is 25. Okay, so for the first car, let's do kinetic energy. I think this is where we need to go with this. So half times mass times speed squared. Okay, so we plug in 1,000 kilograms for the, can you see that? Okay, 1,000 kilograms for the mass of the car, and the speed is 25 squared. Okay, so 25 times 25 times 1,000. 625,000 joules of kinetic energy as it's moving. And so it's brought to a stop, which means if this goes down to 0 when it's not moving, that means all of this kinetic energy was transferred to the thermal energy in the brakes to get it to stop. Does that make sense? Yes?
Weren't you supposed to multiply it by 1/2?
Oh my gosh, I forgot the half. Thank you so much. See, I love when you guys do that because I forget things sometimes. Okay, times 25 times 25 times half. Thank you, thank you, thank you. So that is 312,500 joules of energy. Okay, so as it's moving at its highest rate of speed, this is how much energy it has. We bring the car to a stop, which means this 312,500 joules of energy goes down to 0, and all of it should be converted to the thermal energy of the brakes. Okay, so thermal energy in the first one is this. Okay, the other travels, I think the other one we have to do gravitational potential energy. The other travels down a 300-meter high hill, so that's distance from the ground, at a constant speed and has not stopped. Okay, so GPE, but it's not stopped. Wait a second. If it's not stopped, then there's no thermal energy in the brakes, so we don't have to do anything there. See? So tricky. I start doing all these numbers, and I think that's what they're trying to get at. The other one travels at a constant speed. It's not stopped. If it's not stopped, there is 0 thermal energy of the brakes. The brakes aren't even being applied. Ridiculous. Is it even? Thermal energy. Yeah, I'm just going to go with that. I don't know what this is talking about over here, but if it's not stopping, if the brakes aren't being applied, there's no thermal energy in the brakes. So, I mean, we could still calculate the gravitational potential energy if we wanted to, because what do we know for that? 9.8 times distance, so 300 meters times 1,000 kilograms. We could figure that out, but there's no reason to because it's not being converted to thermal energy. So, does that help? Does that make sense? Okay. Wish I had caught that the first time. Oh gosh, we don't have a few minutes. Suppose that a 110-pound student slowly walks down 3 floors in a building, a total height of 10 meters. What is its GPE? They want us to convert 110 pounds to kilograms. How do they want? Let's look and see how they do that. Okay, so 50 kilograms. See, I don't like when they make you do that either. So the 110-pound student, 110 pounds, is equal to 50 kilograms. So we'll use that. Lost at gravitational potential energy. So GPE is 9.8 times mass times distance. So we plug in 50, and the distance is 10 meters. So 9.8 times 50 times 10 is 4,900 joules of gravitational potential energy. If this loss could be converted into a gain of thermal energy by the aluminum cylinder using what would be the rise in temperature? Oh, for heaven's sakes. Hi, guys. Can you just be quiet for a minute so I can finish this one that I'm doing? Shh. So if we have, you know what? We'll finish this part tomorrow. I'll make a little note here. We'll do this one tomorrow. I mean, next week. Next week. Thank you, guys.
Do you have